Distinguished guests, speakers, ladies and gentlemen, good afternoon. Welcome to the Zero Carbon Forum, co-organized by the World Laureates Association and the Institute of Climate Change and Sustainable Development at Tsinghua University. Our session will focus on how science will lead energy transformation. I would like to thank you for joining us to navigate energy transition for a sustainable green future. My name is Zhang Jian from Tsinghua University, and it gives me great pleasure to moderate the forum. The World Energy Outlook 2022, released by IEA, shows that the world is facing a serious energy crisis, and countries need to develop and implement long-term energy policies in order to achieve net zero emissions and also the global temperature rise control target set in the Paris Agreement. So our forum will focus on the global trend of energy transition and discuss how to lead and accelerate the process of green transformation through scientific research and also international collaboration. First, please allow me to introduce the guest speakers here today. They are Michael Grizel, 2012 Albert Einstein Award of Science Laureate, Professor and Director of the Laboratory of Photonics and Interfaces, EPFL. Welcome. Li Zheng, President of the Institute of Climate Change and Sustainable Development, Professor in the Department of Energy and Powering Engineering, Tsinghua University. I want to recognize that Professor Grizel and Professor Li Zheng are co-chairs of this forum. I want to thank you for convening this event. We have Sang Yamp Li, the 2018 INI Advanced Environmental Solutions Prize Laureate and Senior Vice President for Research at KAIST. Sun Licheng, member of the Chinese Academy of Sciences, member of the Royal Swedish Academy of Engineering Sciences, and director of Center for Artificial Photosynthesis for Solar Fuels, Westlake University. Yulong Ding, fellow of the Royal Academy of Engineering, founding Chamberlain Chair of Chemical Engineering at the University of Birmingham. Carlos Soares, members of the Portuguese Academy of Engineering, and distinguished professor of the Center of Marine Technology and Ocean Engineering at the University of Lisbon. We have Tao Quinn Wayne, professor at the University of California, Santa Barbara, and also director of the Center for Polymers and Organic Solids at the University of UCSB. Li Xiong, professor at the Division of Photonics for Energy at the Wuhan National Laboratory for Optoelectronics, Huazhong University of Science and Technology. Xu Ruina, professor and chair of the Department of Energy and Power Engineering at Tsinghua University. So again, a warm welcome to you all, and we look forward to your speeches and insights in the next 3 hours. Now, let's move on to the first agenda of this forum. And please join me in welcoming Professor Li Zheng to give his opening remarks. Welcome.
Distinguished guests, world laureates, scholars, young scientists, ladies and gentlemen, good afternoon. Welcome to the WLA Zero Carbon Forum. This, as Professor Zhang has mentioned, this forum is co-organized by the World Laureates Association, together with the Institute of Climate Change and Sustainable Development, Tsinghua University. So I'm very delighted to be co-chair of this forum, together with Professor Michael Grizel, who will speak to us shortly. As co-host, please allow me to express our gratitude to all guests and friends present here. I would also like to thank WLA for providing such a significant platform as a distinguished platform for scientific exchange. The WLA Forum plays a vital role in fostering international collaboration and promoting the development of human well-being through science and technology. The theme of this forum is Science Leading Energy Transformation, Energy Transition, and Green Development. In less than a month, the United Nations Climate Change Conference, COP28, will be held in UAE. COP28 will conclude the first global stocktake on the Paris Agreement. The global stocktake is held every 5 years and is a key means to assess the world's global response to the climate crisis and chart a better way forward. However, the way forward is not optimistic. According to the latest synthesis report published by UNFCCC, while there are divergent views on the details of how to reach the goals of the Paris Agreement, governments expressed broad agreement that past climate action has been insufficient and that more actions by all parties and support for developing countries are needed to limit global warming within 1.25 degrees Celsius, to avoid loss and damage, and to adapt to climate change. Energy is at the heart of climate change emergency, and it must be at the heart of its solution too. The intensifying climate emergency, ongoing energy crisis, and increasing political uncertainties around the world are turning points to accelerate the energy transition. Therefore, we have come together at a critical moment as we will focus on the global trends of energy transition and discuss how to lead the process of comprehensive green transformation through scientific progress and international collaboration. Our keynote speeches and panel discussions will fold around important issues of energy transition strategies, policies, and roadmaps, and will dive into the cutting-edge research of alternative energy and the groundbreaking technologies, and will look at the prospects of new energy industry developments. Science has never made humanity more capable of solving the climate challenges as today, and it is imperative to place our trust in science and explore innovative solutions. I hope we can all use the opportunity to navigate energy transition for sustainable green development and to accelerate the process of comprehensive green transformation through scientific progress and international collaboration. I hope you will enjoy the keynotes and the discussions and find the forum thought-provoking. Thank you.
Thank you, Professor Li Zheng, for opening the forum with such a wonderful speech. Next, we'll move on to the keynotes. And I'm delighted to welcome the first speaker, Professor Michael Graziel. The floor is yours, and you have 30 minutes. Thank you.
Ladies and gentlemen, it is a great pleasure and honor for me to be invited to this WLA forum, and I'd like to thank the organizers for having charged me with presenting one of the keynote lectures, and also to co-chair together with Professor Li Cheng this session. And so, my talk will be on actually, this general title is, what are we doing beyond the oil? Oil has come down and new energy technologies have to be developed. And so our approach has been to work on molecular photovoltaics. And out of the molecular photovoltaics, there was the rise of the stunning rise of perovskite solar cells. So I will be talking about, first of all, the quest for renewable and clean energy resources, and then I'll talk to you about these two new technologies. I just wanted to point out to you that we need revolution, we need changes. The incremental approach is not going to work. And so this slide is actually a copy of the slide that was shown by Professor Stephen Chu. He's a professor at Stanford University, a Nobel Prize-winning scientist, and also the former Secretary of Energy of the United States. And so Stephen had told us that we're facing an emergency, and new revolutions have to come in to solve the issues and address the challenges that exist. Yeah, and so briefly, I mean, what we have to do in the next 30 years is to replace fossil resources by the renewables. And photovoltaics has to cover, at the end, by 2050, 30%, 1/3 of the energy consumption. And at present, it's less than 1%. And you can see the pie chart, the pie is also increasing. So actually, the photovoltaics to grow by a factor of 100. And what that means is we have to come in with new technologies and new approaches to meet the challenges. And so, also we have to be quicker than what was foreseen. Just a few days ago, Nature Climate Change published an analysis that shows that our carbon dioxide budget is depleting much faster than what was expected. And so if we continue to emit 30 gigatons or 40 gigatons of CO2, as we have done, you can see that on the slide here. Wait a minute. If we continue with the 40 gigawatt emission of CO2 per year, then we have for 6 years, we have a budget of 6 years, then we would have to go to zero carbon in 6 years to meet the Paris Agreement. And so, this is very worrying. The time scale is much faster than what people have thought. And so, the photovoltaics has been growing, and at the moment we have about 1 gigawatt peak power installed. What that means is about 1 terawatt peak power. It's about 200 gigawatt continuous power. And so, we are at the point where we are here at the point of 2024, we have 1 terawatt installed. However, the curve has to go up to 75 terawatt. And so the question is how to achieve that, and certainly new energy technologies have to come in to support the growth that is required. And so, one of the issues of silicon panels is the high carbon footprint. And so, 50 grams per kilowatt hours, if you translate that on a terawatt scale, at 10 terawatt, you would have 1 gigaton of additional carbon emission. And let's just think about the 75 terawatts that we need. So that would be 7.5 gigatons of CO2 in addition to the problem we have is a 40 gigaton. And so certainly we need lower footprint technologies. And on the bottom of this scale, you can see the dye-sensitized and perovskite solar cells. that certainly our approaches have a low carbon footprint and a very low energy, very short energy payback time. Yeah, and also, I mean, just think about it. To make 1 megawatt of photovoltaics, the perovskite needs 200 times less material than the silicon. And for dye-sensitized, it's 2,000 times less. So from the sheer materials point of view, these are also very attractive technologies. And also then the recycling, we have to think about recycling, and we have to choose technologies that are able to address the issue that comes up as we face now a tsunami of solar panels coming up in the near future. We have to deal with it. We can't put them all in landfills. They have to be recycled. Yeah, so now I come to our journey that our inspiration was from photosynthesis. And photosynthesis uses a molecular approach to harvest sunlight and convert to chemical fuels. And so our inspiration was from the natural system. And we had to innovate. We couldn't just try to mimic the plant and copy it. So the innovation came with the invention of the mesoscopic dye-sensitized solar cell and photoelectrochemical cells. And these have, meanwhile, found applications are commercially produced on a mass scale. However, out of this development also emerged the perovskite solar cells, an amazing rise that has, over the last 10 years, produced over 25,000 papers. And the efficiency being now matching the efficiency of silicon photovoltaics. Yeah, and so let's just see how this worked. So as I said, the photovoltaics uses a molecule, and we know it's chlorophyll, and the reaction I have shown down here. So conversion of CO2 into sugars. It's a good idea if you want to convert CO2, convert to something that is a solid that remains and not a fuel that you burn afterwards. And so the molecular approach which we decided to choose was to sensitize a large bandgap semiconductor, and in this case TiO2. However, when you do that, you have an issue. The issue is that on a flat surface, the molecule doesn't absorb enough light. And actually, the first paper that appeared in this field was a paper by John Goodenough, who later got the Nobel Prize for his battery research. And it showed that the photocurrents were only 70 nanoamps per square centimeter. That's about a factor of 1 million below what a silicon photovoltaic cell produces. And so, at the time we were starting our research, our colleagues discouraged us from going in this direction because they thought it was a hopeless enterprise to get those conversion efficiencies up. And so however, we came from an approach that was unconventional. We were playing with these. We were first to make colloidal semiconductors, and actually the 3 last Nobel Prize winners, they also, at the same time, they came up with these colloidal semiconductors. They then branched into the quantum dots. However, we were interested in using those for energy conversion and studied the electron transfer reactions that are produced by light in those colloidal systems. And so during that time, we found that the electrons that, when you sensitize a system like John Goodenough did, the electron injection in the colloidal systems was much faster, orders of magnitude faster than the recombination. These are very fast events, and on an electrochemical cell, we wouldn't have been able to measure that. However, with the colloidal semiconductors, we could use laser techniques to investigate those electron transfer reactions. And so, and so you can see after several years of fundamental research, curiosity-driven fundamental research, we came up with the idea to use those particles on a support as a light harvesting film. And lo and behold, when we did that, we found a factor of 1,000 increase of the photocount, over 1,000 times higher photocounts than with the flat surface. This was an incredible result. A lot of skepticism first that this was really something people could believe in. However, we showed that it was reproducible, and it's now accepted. And as I said, cells of this type are commercially produced on a mass scale. And so, yeah, so the key of the system is then an array of these TiO2 oxide nanocrystals. It's very easy to put those on a glass by screen printing. And then you dip those films in a solution, and you see the film turns dark red. This is because you have this enormous internal surface area that makes it that even though the colloidal particle is covered with a monolayer, the film itself absorbs very efficiently sunlight. And so that solves the absorption question. And however, in addition, what we found out was that the electrons we inject into these particles, they can be harvested if you design the sensitizer appropriately. And so we see here one example of a ruthenium complex that was applied in these first research papers. And so, yeah, so within a short while, we were able to, with these sensitized system, to produce close to 30 milliamps per square centimeter. That's within reach comparable to what the best photovoltaic thin film and also close to silicon. However, we use 1,000 times less material than what silicon needs. And so that's a real important feature, because cost is important and also the molecular design is important. However, chemists have ideas and solutions, and I'll show you later some of the dyes that were developed. They're very stable and can be applied and give high efficiencies. And so this paper was published in Nature over 30 years ago and has been cited 36,000 times. It shows you that there was a new paradigm that was discovered. And the new paradigm was that we had the three-dimensional junction, the semiconductor nanoparticle junction, instead of the classical PN junction. And so, yeah, here's a picture of Brian and myself. And so we want to set this in motion. So when the light comes in, you inject an electron, and then you collect the charge, and then you have to bring the electron back to the die. And so a redox couple has to be used, or a hole conductor. However, what you can see in this picture is that the distance between the redox level and the die redox level is very large. It's almost half of the light energy is lost in this reaction. So for a while, these cells got only 10% efficiency. And so it was actually the work of Anders Hagfeldt, also Marina Freitag, she's now in the audience somewhere. They addressed that issue and found redox systems that are much more efficient. And so today, we have very high voltages that can be produced with those cells. Yeah, and so let me go quickly. So there's one example of a porphyrin dye where we have a donor acceptor. And the trick is to put the donor at the far end of the sensitizer and attach it at the close end to TiO2, so that under light you have a charge separation that goes over a large distance, so the back reaction is retarded. Yeah, and so here are some applications. Today the state of the art is over 15%. And as I mentioned to you in the beginning, these dye-sensitized systems have produced as a spin-off the perovskite solar cells, which per se have taken their own evolution that has been really amazing. And so, these systems are well known from the material science point of view. They have very interesting optoelectric properties, and also there's a great variety of structures and compositions. So there's lots of opportunities for research. They also are mixed ionic electronic conductors, and so all of this is quite different from silicon. Silicon itself has just one atom type, and not much can be done, if you like, in terms of variation. And so initially, this perovskite was a dye-sensitized solar cells where the dye was replaced by nanoparticles of the perovskite, but they were very, very unstable and low efficient. And then came the our contribution was that to replace the electrolyte by a solid-state hole conductor. And that was known from our work already in the dye-sensitized solar cell field. And so, these are the key papers that were published in 2012. That's just 11 years ago. That's the start of this evolution that went very, very rapidly forward. And so last year, the authors of this paper just saw we almost all received the RAND prize for optoelectronics. And so, so you can see how the number of publications has gone up. And this is a cross-sectional structure, a picture of the structure. And we have still the mesoscopic TI2 as an electroselective contact, and then the perovskite. And the spiro is the hole conductor. Gold is used, but of course in commercial application we will use a different back contact material. And so, you can see that this is a thin film technology, and it uses much less material than the conventional silicon photovoltaic cells. And so, so the latest efficiency in tandem with silicon is 33.9%, and on single materials is 26.1. However, these cells are small, still small. The laboratory cells are smaller than 1 centimeter square. So the scale-up is now at the next challenge, and bring the same or very little losses in these cells when we go to larger scale. And so these are some of the efficiency, the trends we have observed over the last few years. And they're steadily growing. However, now we're plateauing around 26. That's not surprising, because the best photovoltaic cell, gallium arsenide, has 29%. And so we're slowly getting to those limits. Here's some of our work on we were able to, in our laboratory, with the help of Dr. Liu, who's now a professor in Nanjing, and the Korean colleagues, we were able to get to high efficiencies. And wait a minute, let me go back. And you can see the cell itself is very close to theoretical limit. So that's the amazing thing about perovskites. You can use solution processing and get these very high conversion efficiencies. However, what is also very important is the stability. And as I said, the scale up. And so this is the magic triangle of photovoltaics. You have to be low cost, you have to be efficient and stable. And so that the main challenges with perovskites is to get them stable at high temperatures over long periods to match the high stability of silicon photovoltaics. And so initially there were some issues. You can see here the degradation over 350 hours. That's continuous light and maximum power point tracking. So the cell is stressed. However, I mean, they should last much longer than 300 hours. And we can already see a degradation on this time scale. However, this has been addressed, and much more stable systems have been developed. And I'll pass over the details. And recently, the paper has appeared in Nature, where we got very nice stability at high temperature under full light, and also at the maximum power point, where electric field is stressing the cell. When you run a photovoltaic cell, you have to test it at the maximum power point in the current voltage curve, so that you mimic the real life, which means out in the sun you will always try to get maximum power point. And so, let me show you also Li Shong. Li Shong is in this discussion, and actually the collaboration with the group of Li Shong has been exceptional. And over several years we have been working on the science publication, and out came a system that is now scaled up. I mean, here we're talking about larger cells, mini modules, and the efficiency numbers that are given are for 1 centimeter or several centimeters squared, while a lot of other people just take very tiny little cells, less than 0.1 centimeter size. And so yeah, what this science paper reported on was the use of two modulators. One is a redox active dopant for the hole conductor, and the other was an agent, a C60 derivative, that enhanced the cohesion between in the lattice of the perovskite films. And by doing this, the remarkable result was that a new record efficiency was achieved, which I think is a world record at this stage still. I mean, a paper appeared at the beginning of this year, and we can see amazingly over 3,300 hours. And the temperature was 70 degrees. So you have the double stress, high temperature, full light, and you have the electrical stress. That's what you have to do with the perovskite solar cells, to find weaknesses in these systems. And so, yeah, and you can see that the cells degraded by less than 5% over 3,300 hours. Now, what that means is the so-called T80 time. That's the time when you lose 20% of your efficiency. That T80 time is already 13,000 hours. However, the stress, this test is done under stress conditions that are not real outdoors. So there is an acceleration factor of at least 15. So if you multiply 13,000 by 15, you get many years. You'll get 20 years of outdoor lifetime. That's the projection. And so these cells have now the potential to be scaled up and commercially produced. Yeah, I'll have to move on because I have only 5 minutes left. No, 8 minutes. Okay. So yeah, so one of the issues that we still have to solve is that we cannot use gold as a back contact, and so carbon has emerged as a very attractive material. So now the goal is to make the modules, the perovskite modules with the carbon back contact. That's the cheap material, and it's very well tolerated by the perovskites. And so, yeah, we are working with a group in Turkey to set up a production, and there's also a Singapore partner involved. So the idea is to make 30 by 30 modules by pilot scale now. So several groups are now, I would say many are doing exactly the same thing, to set up pilot production, because we have now systems which we can trust. And so it's time to do the scale up and see whether we can make 20% efficient modules. If so, then we can really compete with silicon photovoltaic cells. And so here's an example of an application in Japan. And you can see that the cell configuration was exactly what we had initially invented. It's a mesoscopic film and perovskite, the hole conductor. And yeah, the Japanese company, the Sekisui Chemicals, has the plan to go to the gigawatt scale with that system. And they have shown these flexible devices in an exhibition that was held in Japan. So in Japan, there's also lots of interest activity to scale the technology up and find commercial applications. Yeah, and so we also use the perovskites as a source for photovoltaic, for photoelectric cells. And that's a very important point, because the idea to use the sun to make electricity is a brilliant idea. However, you have to do something with the electricity. And so electric cars are one way to store it. However, chemical storage is preferred. And so if you use the electric power to make hydrogen from water, or you reduce CO2 to other chemicals, to fuels or other chemicals, then you have the sunlight stored like the photosynthesis does. And so this was an initial experiment that was published 10 years ago, where we simply had put two perovskite cells next to each other. And we got already 12% solar to hydrogen. That was a record at this time. And so, yeah, and then the next step was to use a tandem with silicon. And the efficiencies went up to over 18%. And the new tandems, they would produce even higher efficiencies, 25% easily. So you see there is now a track for making hydrogen at a very, very good conversion efficiency. And we are working now together with Professor Chang Hong from Fudan University. We have a project in Saudi Arabia where the goal is to make hydrogen from seawater. That's the next challenge, to use seawater as a source for hydrogen. And in Saudi Arabia, there's a lot of interest all of a sudden in solar hydrogen production, especially from a seawater source. And so, yeah, I'd like to, the last few minutes, I just want to briefly talk to you about CO2 fixation. And so what is the best fuel? Well, there are many options, and so we tested a few options, but from the commercial point of view, the best option is to make ethylene from CO2. And it can be produced now at very high Faraday efficiencies. And it's a feedstock that can be then polymerized and is stable as a solid. So you have taken the CO2 out of the atmosphere, out of the production, like the calcination of calcium carbonate produces CO2. That's a major source of CO2. So you use that source and you convert to ethylene, it's gone. So it doesn't go back in the atmosphere. And so these are very attractive applications that are being now financed by the oil industry. And so, here's an example where we have published with Dr. Denran and Jing Gao, the group leader, our fuel cell group. So that was the first paper where we could show that you can take CO2 to ethylene, just putting our three perovskite cells in series. And of course, with the success of progress of the perovskite technology, efficiencies are already higher today. And so, here's the hydrogen car. That's something that certainly will play a role in the future next to electric cars. And this is Bill Gates. He's very interested in solar fuel production, and he invited Nate Lewis and me to his company in Seattle, and we discussed the solar fuel system. And he set up after this Breakthrough Energy, which is funding the startups that are interested in commercializing the technology. And so, at the end, I show you some applications for our dye-sensitized system. We are very proud that they have reached commercial status, and I want to show you very briefly which applications we have. First of all, there are these panels that have beautiful aesthetic appeal, and they produce electric power for bifacial systems. In sunlight and diffuse light, they're very efficient. This is one application in a facade. This is a disc that was mounted at the Milano exhibition, the World Exhibition, and it had the DSC discs panel. This panel is made of this disc is made of the DSC panels, and it produced 15 kilowatt power, and so that was a remarkable success. So my wife Carol and I we visited the exhibition in Milano, and the electricity was used to drive this truck that was taking care of the forest that was behind the pavilion. And so other commercial enterprises have on their way and producing and selling products. And so one of the very successful ventures is the Exeter in Sweden. They have already 2 plants in production, and these are some of the products like ambient light harvesting with the earphones. You don't need a battery anymore. And so, so I show you now one of the films that I visited the production site in Sweden in May this year, and it's just a couple of seconds. This is the the amazing feature is that they make in this plant 2.5 million square meter per year of the solar panels. And these films, the flexible films, are then used in all sorts of products that power electronics from ambient light. Yeah, and finally, we use our invention to get the young people motivated, and so they make their own solar cells with natural dyes, and this shows that we can go to the very young generation, that we need to infatuate the young generation to pick up and get involved in this challenging task to convert sunlight to electricity and fuels. My time is up, so thank you for your attention.
Oh, thank you so much, Professor Grazel, for your wonderful speech. And it showcased how science research accelerates energy transition. Thank you. Please take a seat. And next, let's welcome Professor Sun Licheng from Westlake University to present. Thank you.
Okay, thank you, Chairman. Also, I would like to thank the organizing committee of WLA for kind invitation. This is a fantastic event. I have listened to several talks and panel discussions. Personally, I have learned a lot. So for this forum, the WLA Zero Carbon Forum, so I would like to show a topic on the catalytic water splitting for solar fuels from natural to artificial photosynthesis. Actually, Michael Grass already touched a little bit in your talk on the fuels, green hydrogens. So probably I can present a little more. If you have a look of this carbon dioxide concentration in the atmosphere, this is observed from Hawaii in the island of Mauna Loa observatory. So you see, since the beginning in 1958, at that time, the carbon dioxide concentration is around 310 ppm, and up to now, you have about 220 ppm. So there's no trend of decline. It's always going up. So this is the years, last year and before last year, you see increasing stepwise, day by day. And if you look at the global temperature at March this year, it has increased 1.48 degrees centigrade in comparison with the pre-industrial period. And it became the second warmest March since 1880. So this number is terrible. So you know the global temperature we try to avoid is 1.5, and this is already reached here in March this year. So we need to change, and also fit to the theme of this forum. The transition of classical fossil fuels to solar fuels might be a good choice. So how to do solar fuels, how to generate the solar fuels. I would like to put up several scenarios for a possible technical solutions to make a solar fuels. So the scenario one I listed here, and again, as Michael Grasso presented, is the catalytic water splitting to generate green hydrogen by, let's say, based on hydrogen and oxygen cycles. So you can do this by converting solar energy into electricity, solar panel, or the wind power or hydropower to electricity. Then you use electrolyzer to split water into hydrogen. We call it the green hydrogen here, and also the oxygen. Here on this specific example, I put up the AEM, so-called AION exchange membrane. So AEMW, water electrolyzer. So PV plus electrolyzer, that's a really attractive way to do. With AEM, the AION exchange membrane, you don't need iridium oxide for water oxidation, neither the platinum carbon for hydrogen generation. The whole catalytic system you can use is a platinum group metal free. So you can see expectedly this technique can develop water splitting with a very cheap price because you don't need heavy metals. So this is the scenario one. And the second scenario is try to reduce carbon dioxide into methanol, for example, here, or you can produce other chemicals like ethylene or propanol. Here you can make the carbon cycle, use the the CCUS to capture the carbon dioxide, and use the electrolyzer again to reduce the CO2 into carbon or carbon-2 plus chemicals. Again, you use a sustainable energy system, solar energy, wind power, hydropower. Here you have several challenges, of course. You need to create a highly efficient catalyst for CO2 reduction, and also you need the selectivity problem. So it's CO or methanol or ethylene. The third scenario I would like to propose is try to make a catalytic nitrogen reduction for a green ammonia production. And this is based on nitrogen cycles. Here on this slide, you can see, you can imagine in the near future, maybe you can make agriculture greenish. And this is a mini factory to produce fertilizers on site for agriculture, okay? Since the atmosphere is dominant with nitrogen gas. So you can use the sunlight, wind power, and you can use a small scale electrolyzer to make ammonia, or even in combination with the CO2 to make a nitrogen plus CO2 to produce urea. That's mainly the fertilizer for green agriculture. If I'm seeing the last or the fourth scenario for catalytic biomass upgrading for solar fine chemicals. This is based on biocycles. Here on this left slide, you can make oxidation for the biomass. So give you example is so-called hydroxymethylfurfuran oxidized to different dicarboxylic acid, which is a monomer for polymerization of PTF. We can replace the PTE. On the reduction side, you can make a production of the hydrogen, also green hydrogen, because the water is involved in the whole process. So far I've showed you 4 scenarios or 4 technical solutions in the future, regardless of which one, either you produce hydrogen or methanol or ammonia or even redox couples by biomass upgrading. Even you can make amino acid driven with the sunlight. You see, all these reactions, they need electrons and protons. So it's a reduction reaction, right? To make the product green or make the process green, you need the green electrons and the green hydrogen. That's the key point. So how to make a green hydrogen and green methanol, green ammonia? The way to do is you generate the green electron and the green proton through the water splitting. And you need a sustainable energy system such as the light. So to do this reaction energetically, it's a very high energy you need. So you need a catalyst, regardless of photocatalyst or electron catalyst or photoelectron catalyst, you need a catalyst. And you need a highly efficient water oxidation catalyst to do this. So we can learn from nature. Actually, nature already gave us excellent examples to do so. So for example, in nature, they have a photosystem 2, was created by nature since 5 billion years ago, really long time ago. Those processes for human beings really can learn a lot. So if you can look, how does nature do the water oxidation to produce green electrons and green protons, you can check the photosystem 2 here. So upon the light irradiation, this catalyst can activate the process. The electrons transfer through another system called photosystem 1, right? And this further transfer to another enzyme to produce NADPH. Through water oxidation, you generate the green protons, and these protons form the proton gradients across the membrane, and then you can make an ATP synthesis, okay? Together with NADPH and ATP, you can drive in a dark reaction for CO2 reduction, for ammonia production, and for other processes in the biological system. So here, you may wonder, what is happening here? Is there any catalytic process to generate water splitting? Yes. Researchers in the world span decades try to understand what is going on in nature, and it turned out that the catalysts look like this color. It's like a twisted chair. It contains 4 manganese, 1 calcium, and the rest are bridged, oxo bridges. Okay? This is a natural occurring catalyst for water splitting. So far, the structure is clear, no problem. What is remaining unclear is the catalytic mechanism. How does it do this reaction? We call the reaction mechanism for ore bond formation. In other words, how does nature do the water oxidation, water splitting? You can see this catalyst can start from a low oxidation state. We call it the S0 state. Okay? Then, upon first proton-coupled electron transfer process reach S1 state, further S2 and S3. From here, S0 to S3, more or less the scientists agreed. It's no problem, no debate anymore. What is remaining, the secret nature kept, is what happening on the last photo process. Upon last photo process, you generate a tungsten radical. And S3 tungsten radical, we found that is first is a proton come out, generate S3 prime state. What's the structure? It's a question. Followed by an electron transfer, you generate S4 state, and also a question mark. And finally, O2, the oxygens involved from nature. The second water come in. By the way, the first water come in between S2 and S3 state. And then you finish. The catalytic cycle is finished. You see here, these two question marks are still remaining. So recently, we have found that upon last photo process, you generate S3 tungsten radical state, the catalytic structure from open to closed Cuban, and from closed Cuban to the open structure become reversible. And this finding led us to have a further observation that the ore bond formation in nature might be occur during these two oxygen atoms, so O5 and the W2. This can form ore bond and oxygen release as occurring dynamically downhill. So far, I would say the water oxidation or ore bond formation mechanism in nature is still not fully understood. So more experimental evidence is needed. So nature spent, let's say, many years through 0.5 billion years ago, developed such efficient catalysts, and it still kept the secret. So what should we do in lab? Can we really make a man-made a catalyst for either homogeneous or heterogeneous catalyst in the lab? That's the question. I was lucky, about 28 years ago, I was involved as a pioneers involved in the construction of the Swedish Consortium for Artificial Photosynthesis. People consider this is the first national team in the world aiming for carbon neutrality, okay? Now it's spread everywhere, okay? But 28 years ago, imagine, at that time, carbon neutrality was that. Never heard about that, okay? So this is the thing I was involved a really long time ago. At that time, what we are thinking to do, try to mimic the core structure, the catalyst in nature, from synthetic in the lab. Although we can do this from the synthetic model in the structure-wise, very close, let's say 90, even 95% structure similarity, if you consider only the first coordination sphere. However, it does not work as nature does. So in my eyes, it does not work at all. Even you can make the synthetic in the lab, 99% similarity, still, you miss something, it still does not work. Then after decade, we have suffered a lot. Then we decided to change our strategy. Okay, we moved from biomimetic approach to bio-inspired chemical approach. By doing so, we have developed so far the most efficient homogeneous water oxidation catalyst. That is called ruthenium BDA. Okay, that's after this ligand. In comparison with 40 years ago, T.J. Meyer reported the first blue dimer under the conditions of semaphore pH 1 aqueous solution. They found the TRF, turnover frequency, TRF, is only 0.004 per second. The water oxidation efficiency is extremely low. Okay, you don't see the bubbles at all. After 40 years, the discovery or synthesis of our ruthenium BDA catalyst led us to have the TRF is more than 1,000 per second with the TRN number, turnover numbers over 100,000. So if you can look at the movie, you need only one drop of the catalyst into the aqueous solution. Then the water oxidation starts. Violently involvement of the oxygen gases. Okay? So you may wonder, this efficiency can we really compare with the naturally occurring water oxidation catalyst? Yes. In nature, it does 100 to 400 per second in nature. Okay? In our case, it's over 1,000. Consider different pH conditions and different potentials. Our systems really start comparable with natural occurring, and sometimes even better, more efficient than nature does. So we have made a tailored design of the ligand. So make this ruthenium BDA from ruthenium BDA to ruthenium TDS. Now, this is the most efficient molecular water oxidation catalyst so far reported under applied potentials. You see, this is a ruthenium BDA in the green color, and the red one is the ruthenium TDS. We do know that the details, how this catalyst can catalyze water oxidation, how the oil bond is formed. Okay, I turn from homogeneous catalyst to heterogeneous catalyst. The way we did is we put a carbon ion into the cavity of a calf. Okay, this is the material. And then, under neutral condition, we found the oil bond formation still followed the intermolecular interaction. However, if you move alkaline condition, extremely high pH, the rate limiting step is non-proton coupled. That means the oil bond formation is occurring within the same metal center. So it's a single atom, it's a single metal cast. So Professor John is sitting in the audience. This is a real single metal cast. The mechanism of oil bond formation here with a three-member ring as intermediate. As you show here, carbon 2,3 and 3,4 and very high catalytic current. So I try to summarize the molecular water oxidation catalyst, material catalyst, or you call it a homogeneous or heterogeneous catalyst. They share a similar oil bond formation pathways for either WLA pathway or intermolecular radical coupling pathway, or as I said, the last one is intramolecular nucleophilic attack pathway happening on the same metal, on the single metal. Why this is important? It's important in different aspects. So first, you can lead to the man-made catalyst for highly efficient water splitting. Another way, you're thinking, try to uncover the secret that nature kept 3 billion years. Professor Michael Greiser already in his talk showed a little bit the photoelectron chemical driven water splitting. Okay? So this is a classical semiconductor that people already considered during the past decade, and perovskite is not so much touched. And now, recently, we have chosen Fa lead bromide. This one with band gap 2.2 eV, which has a strong driving force of water oxidation. We made this photoanode. The photoanode we made is on the conducting glass. We have the tin oxide. Then we have this perovskite, the yellow colored. The perovskite as a light absorber. And on top of the perovskite, we have the carbon, we have the graphite, and we have a nickel iron alloy. On top of alloy, we have this OER catalyst, water oxidation catalyst, nickel iron layer double hydroxide. This is how it looks like from the glass side, and this is from the catalytic side. Okay? We have the seal, the whole process of perovskite, is very dangerous put into water. So we have to seal it with epoxy resin. And then you can dip into the water, and it works. Okay. In comparison with the classical semiconductors like TiO2, tungsten oxide, iron oxide, bismuth vanadate, even thallium nitride, you see our system based on perovskite has a higher current density. Not only that, the onset potential, the bias applied, is really low. Even at 0.2 watt worth reversible hydrogen electrode, you already started very high current, which you cannot get by other semiconductors. So this is a really impressive result. So I have last minute, and I would like to show you, as I said, the AEMWE with industrial scale current densities. For the short term, as I said, if you really want to produce green hydrogen in a big scale, I would suggest you to go to the PV plus electrolyzer approach. With this approach, you can have the sun, solar panel, the wind power, generate electricity. Then you can use the electrolyzer to split water. Here again, I have pointed out in the beginning, in the middle, you can use AEM. That's AEMWE. Because with this setup, you don't need any iridium, ruthenium for water oxidation, neither the platinum for hydrogen generation. You can only use iron, nickel, and molybdenum. Those earth abundant elements to drive this reaction. Then you can reduce the cost dramatically. Okay? The way we did is not published yet. I would like to share these preliminary results with you during this forum. This is the nickel form. We simply use a technique, very cheap technique. We can produce the water oxidation catalyst at this side in the lab. It's a 20 centimeters square centimeter. You see, this is really big size of the catalyst. With this, we call the S1 catalyst. It has very sharp. You see, this is a catalyst performance in comparison with the nickel iron layer double hydroxide, and this is a classical iridium oxide-based OER catalyst, and this one is the nickel form. So this one has a really small, tougher slope, and very low overpotential, and high efficiency, validity efficiency. In terms of the material cost, more or less you don't count it anymore. It's really, really cheap. So how about the performance and stability? This is the comparison of performance and stability test. Here, iridium oxide under 1 more potassium hydroxide room temperature at current density is 1,000 milliamp per square centimeter. Okay? You see the bubbles, the hydrogen bubbles a lot. And it does not keep long for iridium oxide, and neither for the nickel iron layer double hydroxide. However, with our catalyst, with this one, we have tested, it's over 10,000 hours. So it's longer than 1 year, continuous test. It's still running in the lab, okay? It's still stable. So this really provides a hope for future catalytic performance. We have even went further. We have assembled those catalysts with AEMWE. In the middle, we have the membrane, ion exchange membrane. And then we have the iron 1 as the OER catalyst. We have nickel molybdenum as the HER catalyst. Then we put them into the flow cells, you see, flow cells. Then we have tested in the size, in the cell size of 1 square centimeter up to 1,800 hours. And even we put it to bigger size, 25 square centimeters, we have tested with a 25 amp. So square centimeter, 1,000 milliamp square centimeter as a current density under room temperature, one more potassium hydroxide, and this lasts already for 1,200 hours. So this really brings the hope for the energy transition, how to make solar fuels in the cheap and the big size in the industrial scale. This is the final slide. I want to conclude that the solar fuels can really make a sustainable energy transition, and water oxidation, of course, will play an initial role for a carbon neutral society. So thank you again for your attention. I would like to take this opportunity also announce that the first Westlake Forum on solar energy conversion and catalysis is going to be held at next weekend in the campus of Westlake University. So you are welcome, and thank you for your kind attention. Thank you.
Thank you very much, Professor Sun, for your wonderful presentation and also the warm invitation to your forum. Next, let's welcome Professor Sung-Yum Lee from KAIST to give his keynote speech.
Thank you. First, actually, I do have a microphone with me. I don't need this. I can use later. First, I want to thank the organizers for kind invitation. We heard great stories by two previous speakers on solar energy and solar fuel, and we have other important categories using biosystem. So my talk will focus on biofuels, even though I, in general, work on bio-based chemicals, including biofuels. So if you look at the world energy production level as of this year, we are producing about 27 billion megawatt equivalent hours. And out of that, about 26% is renewable based. And if you look at that renewable energy, obviously most of them is hydropower, while wind energy is next. And about solar energy and bioenergy takes about 10% each. So why do we need biofuels? I mean, for example, if you look at the cars, they are electrified now. But in fact, by the year 2050, we're going to still have more than 50% of cars not running on electricity. You can calculate that. And also, if you look at the airplanes, which many of foreign colleagues came to China by, obviously you use jet fuel. You cannot fly with batteries. You cannot fly with SMRs. So jet fuel is going to be around for a long time. So we need to replace petroleum-based approach to produce such hard-to-abate energy sector. And biofuel can play some roles. And the plant we use for the production of biofuel is microorganisms. Tiny, tiny, invisible factory that eats up almost anything and then produce whatever chemical you want to produce, in this particular case, biofuels. But when you isolate these microorganisms from nature, their performance is not good. So you have to engineer them, and we use a lot of different tools of systems biology, synthetic biology, and even laboratory evolution, and integrate all with metabolic engineering that can be defined as purposeful modification of cellular network to overproduce what you want to produce. So that's where systems metabolic engineering comes into play. And one of the very typical biofuel is, of course, bioethanol. Why bioethanol? Well, because we have been drinking ethanol for a long time. So, for example, in China, you have baijiu, right? So baijiu has 55% alcohol, ethanol. Why not 100%? Why aren't you drinking 100% ethanol? And what happens if you drink Beju? You will know exactly where your digestive tract is, right? It's going down and you feel it. Why? Because ethanol absorbs water. So it's hygroscopic. And by definition, fuel should not like water. That's why ethanol is not a good fuel. To begin with, it has lower energy density than ethanol because it's only 2 carbon with hydroxy group. Can we make better chemical that can be mixed or replace gasoline? Well, there's 4 carbon alcohol, which is butanol, which is much less hygroscopic, and also the energy density is similar to gasoline. The problem is it is quite difficult to produce, but there's a bacterial family called Clostridium. Full name is Clostridium acidobutylicum. It basically eats glucose, sucrose, xylose, whatever carbon source you feed, and then it runs the acidogenic pathways to produce acetic acid and butyric acid. And because these acids become toxic, they uptake these produced acids using CoA transferase and convert them to butanol, acetone, and ethanol into approximate ratio of 6:3:1. So if you look at butanol, it's great fuel. Ethanol, not such a great fuel, but you can use it. Acetone is not a fuel. So we wanted to delete it by knocking out and doing pathway engineering. And then unfortunately, we deleted butanol production together. That's because of very complicated cellular regulatory mechanism. But instead of getting rid of acetone, we converted it by introducing one enzyme to convert to isopropanol. So now after the fermentation, you produce beautiful fuel mix. After successfully producing butanol to high concentration with high efficiency, we thought about why just don't we produce gasoline directly? So we engineered the cells, especially fatty acid metabolism, and make the carbon length of fatty acid to the range of gasoline. And then we had to introduce 3-step noble enzymatic pathway reactions into the cell that compose of the CoA synthetase and also reductase and decarbonylase, and then we were able to produce gasoline. And then obviously, if you look into the future, gasoline is not that much in demand because the cars are electrified. But you still need diesel for high-duty vehicles and also jet fuel. So we turned our intention to fatty acid-derived products. So of course, free fatty acids are everyday, chemical you use for food and other applications. And FAME or FAEE are great biodiesel. And jet fuel, we need this for the next 50 years at least. Fatty alcohols and healthy cooking oils. All these are, derivatives of fatty acid metabolism. Currently, biodiesel is produced from vegetable oil or waste cooking oil and animal fats, mostly from plant oil such as palm oil. The problem is that palm oil is a great food compound in East Asia, at least. So there's a food versus fuel issue. And also it requires a lot of land, and there's a land use change that also contribute to climate change. So you're asking yourself that, why am I using palm oil to produce biodiesel to start with? So there should be another way. So we turned into this bacterium that eats anything, including CO2-derived chemicals, and then convert into this huge monster oil drop inside the cell. So basically, the bacterium fills itself with oil by engineering the metabolic pathways. And then you can generate the procedure for the cultivation, and then you can produce these oils to very high density per liter. And also you can engineer further by introducing several different pathways, knocking out some of the pathways you don't want to have, and then you can produce free fatty acids to the concentration you want. So in this particular case, as a proof of concept, we produce more than 50 grams per liter of fatty acids. And then also you can convert it to diesel by introducing new pathway for the formation of ethanol, and then wax ester synthase will condense fatty acid CoA and ethanol to form fatty acid ethyl ester, great biodiesel. Also, you can produce by fed veg culture to higher concentration, and of course, now the titer becomes higher by further optimization. You can also produce long-chain hydrocarbons that's suitable for jet fuel, and of course, I'm not going to go into detail on the enzyme names, but you can design the metabolic pathways for the synthesis of long-chain hydrocarbon directly from non-edible lignocellulosic biomass-derived carbohydrates, or even the simple chemical derived from CO2 using the technologies disclosed by two great previous speakers. So we can produce all these, and now we have optimized the procedure. Look at the gram per liter here. This is quite high, so now we're producing 100 gram per liter of jet fuel directly from glucose or sucrose or xylose. Having thought about this, why don't we just produce these chemicals and fuels directly from CO2? I mean, you already heard great talks by two previous speakers. We have technologies. So obviously you can integrate with living cells. But unfortunately, CO2 should be dissolved in water, and the solubility is very low. And cells are in the aqueous phase. So the transfer rate limits the production rate, which is money. So what are you going to do? Well, one way is that convert CO2 to something that cells like more than CO2 itself. That's formic acid. And as you know, formic acid can be very efficiently converted from CO2 by the various technologies, and it provides electrons. And electrons are needed. Cells cannot grow solely on CO2 because there's no electrons. So CO2 and formic acid together will allow cells grow. But it is not easy because cyanobacterium, microalgae are the only ones that grow well on those carbon sources, but very slowly. And that's not the productivity you want to have. You want to have much higher productivity. So what we did was, among the several designed pathways, by the way, these are the designed pathways by computer-based retrobiosynthesis and all the other tools. And to make a long story short, we basically used reconstructed tetrahydrofolate cycle, where two molecules of CO2 go in, and then it is linked to reverse glycine cleavage pathway that converts the intermediate into one of the amino acids, serine, and then serine goes into a pyruvate, and then there's gluconeogenesis to make all the cellular material and also run the TCA cycle. Here we found that gluconeogenesis is limited, so we had to engineer further, and also we found the cells are limited with the redox power in the form of NADPH, so we amplify the pathways. Now we were able to grow E. coli, which do not grow on CO2 or formic acid alone. Now cells grow on those carbon sources. But again, the growth rate is quite low and have a long way to go. So in the meantime, we are urgent. That's why we have this net zero forum today. So can we make a process faster? So we decided to use a two-component system, where one is the electrolyzer, and out of the electrolyzer, which basically composed of the tin catalyst coated gas diffusion electrode, where CO2 is efficiently converted to formic acid. And then we designed electrolysis solution very carefully so that this same solution can be used to grow cells without giving harms. So formic acid formed from CO2 is going into the fermenter, where cells are happily growing and also producing, in this particular case, plastics. And then this is circulated through the membrane, in this case, hollow fiber membrane. Electrolyzer goes back to this tank. So this is semi-closed system. And cells go back to the fermenter to continue to produce plastics. And we were able to fill the cell up to 83% of cell weight with the plastics from CO2. So this kind of approach can be used in the meantime. Other than fuels, can microorganisms contribute to reduce CO2? Well, many different ways. Actually, in this morning, I talked about the production of various petrochemicals using microorganisms. But here we have another story. If you look at the meat consumption, human beings consume huge amount of meat, 300 million tons per year. That's equivalent to about 38 kilogram per person, where some people eat 70 kilogram, some people doesn't eat, but it's on average. And it releases about 3 billion tons of CO2 equivalent, which is not good. And if you want to produce 1 kilogram of beef, it consumes energy, water, huge amount of it. So it's 7 kilogram cereal equivalent of energy, plus 100,000 liter water. This is just too much. So there have been much interested in producing alternative protein. And there are several companies who make alternative proteins out of vegetable protein or texturized vegetable protein, TVP. And one of them is Impossible Food. And if you have tasted it, it's not quite like a real meat, but it's much better than previous artificial meat. And it's actually similar, and if you do not pay attention much, you cannot distinguish. So what is the key ingredient here to give the meat flavor? Because texturized vegetable protein has been around for a long time, but I hated it because it's a fake meat, we call it. But now it's much better. And then it was found that the flavor, meat flavor, was given by heme in your hemoglobin. Okay, well, if it's heme, why nobody produced heme? Because it's difficult to produce. It's a long pathway. The heme itself is very toxic because it kills a lot of enzymes inside the cell. So we had to optimize the entire pathway enzymes, expression levels, and then identify the exporter so that we can pump out heme so that it is no longer toxic to the cell and cells happily continue to produce. And then we were able to produce large amounts of heme. If you look at the fermenter here, the E. coli producing heme is already blood color because it produces a lot of heme. And as the time goes by, of course, it becomes really dark brown. And this was the initial publication we reported, showing that this process can provide enough heme for providing lots of artificial meat or alternative protein. But we further improved it for commercialization, and now we produce more than gram per liter quantity, and also more than 2 gram per liter of zinc protoporphyrin, which adds additional flavor to the alternative proteins. So this kind of approaches can definitely contribute to the net zero, together with the technologies presented by 2 previous speakers. But here biotech can play an important role as well, because you have microorganisms here, and you feed them with C1 gas or waste, such as food waste or lignocellulosic biomass-derived carbohydrates, and then metabolically engineered cells will produce bulk chemicals, fine chemicals, food additives, drugs, whatever chemical you want to produce. And of course, this is not the end of the story, because you can combine this with other chemical processes together. So take intermediates, convert further using chemical catalysis, and then you can produce many different chemicals that used to be produced by petrochemical industry. So I think biotech not only contributes to the biofuels, such as butanol, gasoline, biodiesel, jet fuel, even hydrogen. There's a biohydrogen you can produce, but in addition to that, you can attack staggering $4.8 trillion chemicals market. How fast we're gonna move, we don't know. But I would assume that by 2050, at least 25% of that huge market will be bio-based chemicals. Especially if you look at the trend in Europe from a long time ago and trend in US recently, that's called Biomanufacturing Initiative. Everybody's crazy on producing bio-based chemicals for obvious reason. We cannot just rely on fossil resources anymore. So with that, I want to thank your attention and also thank my group members who did all the work. Thank you.
Thank you very much, Professor Lee, for your excellent speech. Without further ado, let's welcome Professor Yulong Ding from University of Birmingham to speak. Thank you.
So I'll stay here and then the microphone. So my talk is going to be on most on the energy storage area, and I want to bring back what as scientists, what scientists are going to do and what engineers are going to do. I'm an engineering scientist, so I'm looking at more practical aspects. Think about technologies which is for net zero 2050 or 2060 or 2070. If technologies are not already developed, it's too late, because any technologies would take decades to get to the market, applied in large scale. So first of all, I want to say climate change is very old science. Actually, more than 100 years ago, Joseph Fourier and also Arrhenius were already, talked about that. There's a theory about that. So that's first I want to say first. Secondly, climate change is real, and of course there's still debate on if it's real or not. But I think that all the evidence point to it's real. So it's too late to debate on that. I think that we have to base on evidence. That's what science tells us. Thirdly, I want to say global warming is actually originated from the very small amount of greenhouse gases. And it's not only a carbon issue. Carbon is one of them. And actually, if you look at this table, the carbon, if it's one, this is from 100-year time horizon. So carbon is one, then a lot of better guys, which are more challenging to do. So what I'm going to say is that carbon neutrality is more or less an energy transition issue. It's an energy issue because more than 73% of carbon emission is from energy sector. So without getting this done, then we can't achieve that. So that's the third message. So last not least, the global energy sector, as I mentioned, contribute over 70% of gas emissions. But within energy sector, if you look at the distribution of those, so industry contributes about 30% of carbon emission, and the transport 16%, and building 17%. So if you look at the road transmission, CO2 emission for road transportation, which is biggest, rail, aviation, shipping is very small. So people blaming jet fuels, using jet fuels, airplane traveling is probably the wrong. It's important to contribute, but actually it's not the most important part. So the most important part is industry, which is really hard to do, and road transportation, and also commercial, which is building. So with that, I'm going to look at three aspects. First, what are actually the main challenges for energy transition? I'm going to look at 2050 to 2060, and what are the current new and emerging technologies meet the net zero target? That's the second question I'm going to try to answer. Thirdly, what are opportunities for energy storage, which is main in my area. I'm not talking about my research much, but what I'm going to convey the message is our energy infrastructure was designed 100 years ago, and they cannot deal with issues we have today. So how do we do that? So look at the main challenges. So if you look at what systems we have today, the particular energy conversion and utilization chain. Today, heat is central because thermal energy accounts for 90% of the energy conversion, storage, and transmission. In 2050 or 2060, it's going to be in the center as well because of the amount, the percentage will reduce, but we have to meet our energy consumption. So what I'm going to say is that fossil fuels today, they have energy storage functions. We don't need energy storage much. But 2050 to 2060, renewable energy doesn't have the energy storage function, and hence we need a storage. So that's first aspect. Then secondly, what I want to say is that if you look at our global final energy consumption, heat and cold account for more than 50%, transport 32%, and electricity about 17%. If you look at the percentage of renewables of those, electricity already, probably around 30% already. It's not that challenging to get that down. But the thermal, heat, and cold transport are challenging. So whatever you do, our challenge is that how do we meet the final energy consumption, because that's our living quality, and we can't do without that. So, and another thing this diagram is drawn by myself, which is from bottom to top, from fossil fuels today and in the past to future renewable energy. From left to right is primary energy sources to final energy use. So what I want to convey the message is as follows. First, in the past, today or the past, we have a couple of energy conversion steps from the energy source to final use. We burn gas, we burn coal, we burn oil, we get heat, and we use the turbine, expand, we get electricity. So that's 2 or 3 steps. But in the future, we might need 7, even more steps. We know every step we have energy loss. Those energy losses become heat. As I just mentioned, our final energy consumption, more than 50% is for heat, for heating. And cooling is important as well. I'll mention that later on. As a result of that, of course, people would say renewable energy is cheap, is free. But the problem is you have to use more land, you have to mine more materials, and you have to invest more. That's not sustainable. So that's the important things. How do we make use of waste heat in parallel to the use of renewable energy? So essentially, the use of renewable energy for net zero is essential for net zero 2050 or 2060. But the use of waste energy is equally important because there's 2 sort of aspects we have to bear in mind. And our energy infrastructure have not been designed to account for that. That's a major challenge. If I want to say one more, it's about the global energy demand for cooling. This diagram was put forward nearly 20 years ago, 50 years ago. So think about, this is for heating, energy demand for heating. Well, more or less, not much changes. So, but for cooling, because living quality is increasing, particularly people from African countries, global south, India, and they're catching up. So the energy demand for cooling around for 2070 will increase to be higher than that for heating. I just mentioned for heating, we need about 50% of our final energy demand. If we don't consider cooling, we would not be able to meet the energy net zero 2050 or 2060. That's a large aspect we need to look at. So moving to the second part, we have lots of technologies. We heard lots of technologies. Can they really meet the current, the 2050, 2060 challenges? So first, this diagram I just mentioned already, clearly because we use renewable energy and we need energy storage, which can be from generation side, can be from distribution, transmission side, can be from final energy demand side. So if I give a few sort of examples to illustrate if the current technologies or emerging technology can meet the net zero 2050 and 2060. So the first is always put forward in electrification of transport. So left side figure is electric vehicles, the measured mileage for different brands, the measured and minus 7 degrees C. Essentially, if the ambient temperature is minus 7, which is in the north part of many countries like China and Canada, probably Russia and other countries. So think about roughly the actual mileage is only half of that of the manufactured, the mileage given manufacturer. So that has been validated in China across 3 loss areas. Essentially, the mileage provided by the manufacturers, roughly reliability or credibility is only about 50 to 60%. So that's why in very cold area, electric vehicles, rarely you can sell that because it just can't be used in winter. Because batteries need a temperature to have reactions. So also, if you look at the country like Singapore, cooling demand is high. So in big buses, coaches, the power consumption for cooling probably accounts for 50% of power. And hence, you also have issues. So with that, also I want to mention is that onboard air conditioning technologies has been used for nearly 100 years. Well, so, but onboard air conditioning units have about COP, which is 1 unit of electricity produced probably 1 to 1.5 units of cold energy. Is this still good? Probably it's not, because stationary system can be 4 to 6. Why can't we use the stored heat or cold energy to replace air conditioning in electric vehicles? It can be done. And we can use a charged approach, like batteries. But electrochemical batteries is for drive the car. But heat and cold batteries is for providing heating and cooling demand. So that's can actually increase efficiency quite a lot. So that's the first example I want to say. Second example is hydrogen economy. Again, this can be controversial, but this is not my data. My data is similar to this, even slightly lower. I use the data from DNV, which is a Dutch organization. So essentially, hydrogen production for electrolysis is probably about 40%. Transmission, distribution, storage is about 20%. Final energy use, if we use fuel cells, probably about 40%. This data shows us if we use a centralized production and distribution and use the hydrogen using fuel cells, then energy efficiency would be probably less than 5%, 40 times 20 times 40. If we produce locally, use locally, it's about less than 20%, probably 15%. So now the issue is, how do we address the issues? So I'm not criticizing those technologies. What I'm trying to say is, can we make use of the waste energy for heating and cooling applications? But our energy infrastructure was not designed for that. We need to develop that. So that's opportunities. So third one is CCS or CCUS. Previous speakers have talked about carbon capture and uses the captured CO2 for converting that to fuels and other applications. So what I want to say is that carbon capture consumes about 250 to 300 kilowatt hours of electricity per ton of CO2 captured, and compression with about 100 kilowatt hours per ton of CO2 compressed. And if you have long-distance transmission, then it will consume more. So the issue is, how do we increase efficiency, make use of the energy lost for that? So that's another challenge. We needed that, but radical new innovation is needed. For example, can we use CO2 in the process rather than release that? There are technologies already started to do that, and I don't have time to talk about that. It's actually one of the areas I'm actively pursuing. So the popular area of AI, telecommunication, 5G, 6G communications, this actually produces challenges for net zero 2050, 2060. Let me tell you why. Currently, ICT industry consumes about 10% of global electricity. Data centers consume around 300 terawatt hours electricity per year. And projection for 2030 is 20% of electricity because of AI, autonomous vehicles, and so on and so forth. 2040 is 30%. These are not sustainable, and we can't deal with that. And with the booming of AI, this probably is going to be more than that. How do we deal with that? So next one is about our foundation industry. Matters to all national security for all countries. Foundation industries, metal, iron making, steel making, glass, cement, chemical, and paper making, and so on and so forth. Take steel making as an example. This is the whole process. And steel making accounts for over 8% of global carbon emission. For China, I think it's about 13, 14, maybe 16%, because China produces probably 60% of global steel, crude steel. So if you look at the process, iron making process accounts for 70% of carbon emission. And we know that, produce 1 ton of hot metal would consume 650 to around 700 kilograms of coal equivalent. The theoretical minimal sort of energy consumption is 250 because the second law of thermodynamics. The issue is lots of people don't look at thermodynamics. They probably think about that can be done. It's not the case. So I would encourage sort of everyone think about the second law of thermodynamics, what it can achieve, what cannot achieve. There are lots of things in publications which don't conform with second law of thermodynamics. So that's something which is I want to bring the attention to our scientists here. So, and also the new technology is being developed for iron making, steel making. So for example, the hydrogen steel making, and in electrochemical, for example, typical example is Boston Metal, the new innovation, and the carbon capture storage. And so our assessment is that those emerging low carbon technologies are economically unfeasible today, and very likely remain so in 2050 without more radical innovation, significant investment, and specific policy support. We need policy support for that. Otherwise, we can't do that. So, so last, I think about just a short of 4 minutes, I'm going to sort of look at the opportunities for energy storage. I'm going to skip a couple of slides. I want to sort of convey the main messages. The first is that the national infrastructure for energy. Our energy infrastructure is designed not for today's scenario. It is designed and built around electrical grid and close to power stations, which are not going to be used in the future, or most of them will be decommissioned. For example, coal-powered plant, gas power plant, and oil-based plant. So how do we do with that? So the issue is that, as I mentioned, we are going to have multi-energy vectors. We have electricity, we have hydrogen, we have methanol, we're going to have heat and cold, we're going to have metals, and so on and so forth. So a new sort of design, particularly for the UK, we are advocating a new energy infrastructure, which is a network of local energy networks. Because the future 2050, 2060 is going to be more localized energy networks, local production for local use, rather than for long-distance transmission, because I think it's more efficient because so feature of those, I don't have much time to say that, but I think the issue is that it's going to be less integrated, because less integration, we're going to have lower efficiency. The use of waste energy will be more important. It's going to be multi-energy vectors, and so there are going to be more mobile services, for example, charge-based infrastructure. So if you're interested, we can talk a bit more about that, but I'm going to skip that. Energy storage technologies have lots of role to play. So there are lots of technology of those. I think they're misleading information about installations globally. So, but I'm not going to talk about that. What I'm going to say is that energy storage, give a little bit information in terms of what actually the leads for energy storage technologies. Today, so this is sort of the market leads for energy storage under net zero. So this is what we have today. This is going to be sort of for 2030 projection. So this is in terms of US dollars or RMB. So it's really big. It's exceeding 1.7 trillion in 2032, and with Asia Pacific region exceeding 0.9 trillion. So this projection is, I will show you, it's actually probably is realistic. So in terms of capacity and power, because energy storage, we have two elements. One is power, one is capacity. Power is listed here. Today, we have about 200 gigawatts installation. Capacity for about 30 terawatt hours. And 2030, about 740 terawatt hours projection. So the message here is that the market is huge. So if you look at the market in terms of US dollar, 1.7 trillion, and the demand in 2030, the cost of that would be about 2.3 per kilowatt hours US dollar. It's not a silly number. So they are all making the right. So what I want to say in the future, what's exactly the market needs for energy storage? So don't have time to say the details. What I want to say is that UK Royal Society has done a study to assess UK needs. So the idea is, okay, that's demand in a typical year, that's supply in a typical year. If we take demand from the supply, you get a number. Well, this is fluctuating. Sometimes you have less, sometimes more. You have to store energy. So if you put those, use the past 37 years of energy data, you get those data. Essentially, you need short-term storage batteries, for example, medium-term compressed air, liquid air, and flow batteries. Long-term storage is hydrogen and thermochemical technology. So really is, if you look at global installation today, they are not sufficient for one UK application in 2050. The market is huge. And if I put the last slides for you is that if we use UK's data, which is I think rigorously done over the past 4.5 years, involving 50 scientists, I was fortunate to be a steering committee of that study. So we assume the total energy storage capacity and power scales with energy consumption, which probably is not silly assumption. If we do that, the global energy consumption in 2050 would be this amount, nearly 4,000 terawatt-hours. It's huge. And I think it's more realistic, there's sort of a more scientific data for that. So short term will be that one, medium term was that large, and long term is huge. Of course, medium term can fit long-term storage, and vice versa. So this provides the projection for investors and globally. So, and if I put that in a number, so essentially, we know 2030 to probably projections about 740 terawatt-hours. If we look at compare that with that one, which means 2050, it's going to be about 5 times the 2030 projection. So with that, I'm going to conclude. So climate change is due to the carbon emission mainly from energy sector. We have to address energy sector's issues, and that need energy transition, and it need a global efforts. One country, one company is not going to do the work. So current emerging technologies all have a role to play in net zero, but how to enhance the efficiency, cost effectiveness, and sustainability and infrastructure require radical rethinking, particularly our energy infrastructure. Finally, energy storage is essential for net zero energy transition. The market is huge, it's massive. So with that, I thank you very much. Sorry, I exceeded a little bit time. This is our campus. Thank you.
Thank you so much, Professor Ding, for your excellent presentation. With that, we come to the end of the keynote speeches. May I propose that we give a big round of applause to the 4 speakers. Thank you for your wonderful keynote speeches. And next, we'll have the panel discussion. We spent about 60 minutes on the panel discussion. Let me invite Professor Li Zheng back to the stage to moderate the session. Thank you.
Thank you, Ding Zhang. So now it is time for panel discussion. So we have a very luxury team of panelists. So please welcome Professor Michael Greisel. Applaud. Professor Sang-Ye Li. Professor Yulong Ding. Professor Carlos Soares. Professor Tu Huyin Nguyen, Professor Sun Licheng, Professor Li Xiong, Professor Xu Yuna to come to the stage. So, as we have recognized, this forum mainly focuses on the big trend of energy transformation, discusses how to lead and quicken the progress of comprehensive green revolution through scientific advancement and international collaboration. So we have prepared several major topics or questions. So the panelists are expected to express your views and opinions and undertake sufficient discussions. So I will propose the topic, and according to your research background and your reflection about the problem, and you can take the chance freely. So our first topic is about the research directions in energy and the climate field. So this, I think the audience listen to the keynote speaker's speech. I think they are very eager to learn from you what will be the future directions. We all know energy transition is imperative to battle climate challenge. Then, in energy field, and in accordance to your research background, what research hotspots do you think are worth paying attention to in the field you specialize in? Which technology is more competitive and has the potential to become the future form of energy? So just now we heard a lot from PV, from energy storage, from biofuels, solar fuels. So it's a plenty of choices. So what will be the hotspot for research? And what will be the prevailing technologies that can solve our future problems?
Yeah, maybe I can start if you...
Okay, yeah, please.
Yes.
So,
I would like to suggest, in addition to the solar cells, of course, that the solar fuels is going to be the hot research topic in the near future. Solar fuel is a really broad name or concept to really reach, let's say, zero carbon transition. I think better we start to consider the solar hydrogen, or we call it the green hydrogen. You know, those hydrogen nowadays produced mainly from petroleum, the industry, and that is called so-called gray hydrogen. Well, hydrogen is not color. It's due to the source of production called gray. Although you can try to capture the CO2 during the production of hydrogen, you can produce so-called the blue hydrogen. But again, it's involved the carbon dioxide. To really get rid of carbon dioxide, so you should consider to use a sustainable energy system. As I said during my lecture, you use solar, you use wind power, you use hydropower, and then you split water. And then you can produce hydrogen, which we call it green. So-called green hydrogen is not the hydrogen itself as green, it's rather the energy sources you use. And the process you produce the hydrogen, that should be the greenish. And that's why we call this the green hydrogen. If you make an analysis of economically, the green hydrogen produced nowadays is quite cheap. It's from the coal, from petroleum. It costs likely, in terms of RMB, is like 12 yuan per kilo of gray hydrogen. If you add up with a little capturing of carbon dioxide, so-called the blue hydrogen, you can reduce the, you can increase the cost a little bit, but to produce a green hydrogen nowadays, it's a cost maybe 3 or 4 times higher. Let's say over 35 or less than 40 yuan RMB per kilo. So the future hot research is try to develop a technique how to reduce the cost of green hydrogen. I think that's the main target we are going to do. So,
Green hydrogen, you think
green
that's the
hydrogen,
future?
that's
Okay.
why I said
So,
that.
Michael,
Yeah, definitely. Hydrogen is a future energy vector, and the green hydrogen has huge advantages. However, it's still a little bit too expensive, and so the cost has to come down to about $3 per kilogram, which is challenging. However, it's not unrealistic. But in my opinion, it's true. We have to see that solar fuel is key, and I'm glad that we have now the water oxidation and catalysis has made big progress. We have to use water as an electron source. However, there's also the aspect of the CO2 emission by industry, and the main culprits are the ammonia production and calcination for concrete. And so these are, at least half of the CO2 emissions come from these two industries. And so we have to capture the CO2 on the production side. And that's much easier than to claim it back from air. I mean, once it's in air, it's very difficult, very costly to do. Photosynthesis does it, but I mean, we have way to go to get to this application. So we have to capture the CO2 on the side where it's produced. And then we should convert to something that is storable. And making it into a fuel is not a good idea, because then it's just one cycle further, you will have the CO2 back in the air. And so there's really no net CO2 reduction. And so it's clear that also industry is jet fuel from syngas is an attractive idea. However, even the jet fuel is burned and then it's up again in the air. So storing the CO2 in form of a solid is very important. And I would say from our present experience, I mentioned ethylene in my lecture, and the CEO of Aramco is the same opinion. He thinks CO2 ethylene is the way to go. However, formate is also very attractive, and it's a much easier target. We have submitted a paper where we can make formate at current densities of over 1 amp. If we use lithium-Sun's catalyst for oxygen, that would be just perfect. So formate and ethylene, formate can be used for polymer synthesis, and it's an electron or hydrogen source also, so it's a storage system. So these two vectors, in my opinion, are important.
thank you. Professor Ding.
Thank you. I think we'll probably need to look at these things from a more system approach. So look at first is the short to medium term to meet the 2050 or 2060 net zero target, because it's urgent, and also technologies for beyond 2050. So if we look at, I think short-term priority probably will have to be concentrated on the technology which is either already been developed or sort of in the process of commercialization, because it takes decades for that to be deployed, because the scale is huge, and such a scale is not something you can do within a couple of years or 5, 10 years. It's going to be longer. So that's the first I want to say. Secondly, so bear in mind we have generation side. For example, fuel production is generation side, and we have to have a storage, distribution, networks. Thirdly is demand side management. So we have to look at 3 aspects. As I mentioned, energy infrastructure is based upon 100 years ago, electric grids. So we have to have research on how the future energy infrastructure is going to be, which sort of take those fuels or the energy vectors and store them and transmission them and transport to the end users. So those need to be radical thinking. The third aspect is the energy efficiency, because I think if the efficiency is too low and the material you use, if it's critical materials, there's a bigger problem. So, and geopolitics will be another challenge. So essentially, what I'm trying to say is energy efficiency, energy infrastructure, those are all important. And also we have to look at short-term and long-term.
So because our urgency for climate change is 2050 or 2060. So we have to prioritize what we do. So.
Okay, I understand that. When all the fossil energy are replaced by green energy, renewables or biomass, that is still the carbon budget. There are more carbons in the atmosphere. So we need negative technologies. So Professor Kuo.
I would like to add that I agree with all the statements have been pointed out, but if we want to reach to the net zero, carbon dioxide net zero in 2050, I believe that we need to use different approaches, combination of approach to solve that issue, and which energy generation technology is better. It really depends on where you are, right? In certain area, like I'm a bit biased. For example, if you in the highly density population city, like in Shanghai, for example, and in that case, like I think new emerging PV, like Professor Grasso mentioned, dye-sensitized or organic solar cell, semi-transparent type of solar cell will be more suitable than silicon or other type of technology, right? So it really depends on where you are, that one technology will be better than the other. But we need to utilize everything that we have available to us. Another issue about transportation, and we also have to think about the infrastructure and transportation as well.
Yes, yes. So we are not talking about only the energy theoretically. We need to be distributed and used by people. Yeah, and there are also, that's where we come to my next question. I will talk about that. So anybody want to see more about it? So Soares, please.
Well, I'm more associated with wind energy, which is a relatively established technology. As we saw in the last presentation, wind energy is already contributing with a significant part to the energy needs. So I don't anticipate any revolutionary evolution in this type of energy. However, the present trend is, I mean, at least in Europe, there is a large trend to increase the production of wind energy. And there is a great push to go offshore with this type of energy. So the problem is that the costs are still large to produce and then to transport it. So there is ongoing research on the production of hydrogen at sea using the energy produced by the wind turbines. And this would need also the technology for storage. But I think if this managed to progress, this would be a way of making wind energy offshore much more efficient and have a way of producing hydrogen that could be then stored and eventually even transmitted to shipping directly. So this is a research direction that is associated with wind production offshore and which might bring useful results.
Thank you. Professor Xu, I saw you want to speak something, please.
Okay, thank you. And as mentioned by previous speakers, actually the energy is really a very large field. So I don't think only one technique can solve all the problems. And we'd better to pay attention more on the new technology, but also pay attention to the existing technology, to how to remove the carbon and how to transition the energy form. So if we look at the large terms, such as around 2040, so around 1 billion of CO2 should be removed. So one of the CDR technology of the CCS, as mentioned before, actually is a large-scale technology to remove CO2 from the atmosphere. Actually, we have to face the many problems, such as if we can store the CO2, so much amount of CO2 stored underground, and if it's safety and if it have the injectivity. But we have to say it's a one of the technology to remove so large scale CO2. And for the new technology, as mentioned before, for the hydrogen and the solar technologies are all the new methods to solve these problems, and all new the very promising technology, I think. Thank you.
Any experts, any comments on this topic? Any more? Yes, Professor Ding, please.
So I would just follow the discussion on CCS, because I think the main issue with carbon is just the accumulation of carbon dioxide over the past 200 years. So I think there are technologies which can turn CO2 into CO within the process. So for example, the double perovskite material doesn't contain any critical materials. It's just calcium, barium, iron, and so on. So that can split CO2 to CO with 100% selectivity, but efficiency about 10%. And we tested that material at lab scale. That can work well. If we integrate that in the industrial process, can actually, of course, reactor design would be a big issue, because I think one pass you get 10%, another pass 9%, another pass 8%, and so on and so forth. So, but nevertheless, if that area is to be invested in, and I think that provide a potential route, pathway towards in-process CO2 splitting, and put the CO back to the system rather than storing on underground. So this also provide a potential of turning CO2 stored in the future, large quantities, as a resource rather than as a burden, which we take that as a burden today. So which could be bankable from investor point of view, because you always can turn that into CO, which upon you have hydrogen, you can produce hydrocarbons using various processes, as you guys have mentioned. So I think that's another thing which I just want to mention. And I think that at TR they were about 3 to 4. So I think but I doubt that would be in large scale in 10 years, probably about another 20 years. So that's just want to add to that.
So in China, actually, we have a lot of discussions about the CO2 utilization. So I would like to remind you the scale of the mass. So each year, globally, we use about 4 billion tons of oil, and they produce all the petrochemicals we use and also fuel our cars. But for CO2, we are talking about 20 billion tons per year. So I think conversion is something necessary, but we need also other things. And I noticed Professor Li wants to talk, but I speak a little bit more. So as I mentioned in the beginning, so COP28 is going to happen, to be held in the month. So there's a lot of discussions about CCS. So many people think CCS is something we need certainly to solve our problem, but other people say that CCS only gives the excuse for the continuation of fossil energy. So there are a lot of different opinions. So,
yeah, I think that's a great point, and also all the panelists gave excellent, technology points we have to focus on. So as a person who speaks almost at the last, I have nothing much left to say, but I would put it this way. I think we need, even though I work on biotechnology, I do not claim that biotechnology is the most important technology here. I think we need a lot of different technologies integrated and used as a fully flexible energy mix and utilization system. That's what we need. And for that matter, I think we need to look at the entire system, starting with the sun, of course, but all the terrestrial energy source like hydraulic power and all these things, but also the renewable materials. Plus, as you commented at the last minute, how are we gonna, I don't like the word CCS, by the way. Why do you store? You need to use. So CCU might be a better solution. But in the meantime, you want to convert CO2 to something more interesting, like methanol or formic acid, that can be immediately used. And also for the renewable energy like wind power, solar power, what are we going to do with this energy left beyond utilization? Where people easily say that you develop energy storage system, ESS. That doesn't work. I mean, if you are working on large-scale battery system for energy storage, you will see how monster that size would be. So you have to convert it to chemical forms, unfortunately. You're going to lose some energy during the conversion process, but it's much better than nothing. So all these technologies need to be integrated, and I put it in the way of fully flexible energy mix system.
Yeah. So there's no single silver bullet. So we need a combination of technologies. So, because time is running very fast. So actually my second topic is just a following up of the first one. So, but more specific. Looking forward, we have the so-called hard to abate sectors, like heavy transportation, like building, etc. Heavy industries. So it's hard to abate sectors to decarbonize. And the International Energy Agency tells us that technologies for up to 50% of carbon reduction is still not commercialized. We need great innovation. However, it is not certain what technologies could be disruptive. So my question, so make use of this valuable chance with so many very high-level scientists. So the question is that, what disruptive technologies could happen in the future, and why you think so? That is a challenging question.
Let me start because I talked last for the first question. I think the best and the groundbreaking technologies will come out of, for example, Mike's work on perovskite solar cells. Also, you can integrate with chemical conversion, as I emphasized. So it's not just solar fuel. We heard a great story about solar fuel. But usually, those conversion process involves conversion of C1 compound, that's CO2, to maybe C2, C3, up to C4. But beyond that, you need a more complicated process, which requires a lot of energy to produce. So that's energy used in the chemical industry. That's why, that's where, biotech can go into play. So again, the theme here is now you are integrating solar technology, chemical technology, and biotechnology to address these problems. So I think it's not just single important, killer technology that can solve the problem. But since your question started with the hard to abate sector, and the last speaker briefly mentioned that the aviation industry is only 1% to 2% of carbon emission, and so it's not important. But the problem is that the other 99% causing industry are not changing, while aviation industry is willing to change because they are just shooting CO2 directly into the sky. So this mandatory that they need to change up to 50% of aviation fuel or jet fuel into sustainable fuel. Because how much does it cost? The Boeing 747 is $400 million per aircraft. You cannot just throw it away and, okay, we're going to electrify it. You need to use it, at least for 50 years. Also, airport infrastructure. You're going to change it to electric charging station? No way. There are runaways and jet fuel, supply chains. That's why, at least for the next 50 years, it's going to be very hard to abate sector. So that's why, the renewable-based jet fuel is very important there. And not just the bio-based jet fuel, but also Fischer-Tropsch out of the solar chemical, for example, can be alternative jet fuel that's more sustainable. So all these options need to be taken to solve these climate change problems.
Also electrical aircraft, that's also a kind of solution.
Electrical aircraft is not possible for long hours.
Not for long distance.
Yeah, short distance, but are you sure you want to fly the battery run
You are a
airplane?
scientist.
Not
You're a
me.
scientist.
Even though it's a short distance, I'm not going to fly on the battery plane.
In the last year in Egypt,
Maybe hydrogen plane I would.
I saw a 2 kilowatt in electrical motor. It's just
like drones. Yeah.
very small for 2,000 kilowatt. Yes, please.
But think about the solar impulse. That was really discouraging. This was a Swiss project, the solar impulse, to fly an airplane electrically, and they didn't even make it to Paris at one time because the wind was so strong. I mean, this is way far away from being a commercial reliable technology. However, I feel that airplanes could fly on hydrogen. I mean, the supersonic airplanes do that, and so that would be much cleaner than burning jet fuel. We don't have any CO2 penalty.
But as SAF, as a sustainable aviation fuel, is very important. Yes, Professor Sun.
Yes, you're talking about disruptive technologies for zero carbon transition. I would suggest this AEMWE can become disruptive technologies. Why is that? So far, the green hydrogen generation, there are 3 methods, right? So one is PV electrolyzer, where the PV you can consider as the microaggressives presented, the progress on the perovskite solar cells or combination of silicon with perovskite. So you can really have a really high efficient solar cells to generate electricity. Unfortunately, you know, the sunlight is not 24 hours in the sky, so you need to store the solar energy. One way is to make electrolysis of water to generate hydrogen. We call it green hydrogen. So nowadays, commercially, industry-wise, produce green hydrogen is use alkaline electrolyzer. Okay, the alkaline electrolyzer use earth-abundant elements, and is large scale. Why is not produced at a lower cost? Because it's simply the current density that produces is quite low. Electrolyzer produce, less than 500 milliamp per square centimeter. That's the current density you generated. This need to be improved at least 2, 3, 4 times higher. One way to do this is PEM, so-called proton exchange membrane nowadays people use. The PEM can generate high current density up to 2 amps, 2,000 milliamps per square centimeter. However, the cost is so high, stop the large-scale production. The cost mainly comes from the catalyst and also the polymetals. The catalyst used for water oxidation is iridium oxide. Imagine iridium, not so cheap. And also platinum for hydrogen generation. So this inhibits the large scale production. Nowadays, this new technology is coming up, and that is called AEMWE. In this way, we can move from the PEM, which is under neutral condition or acidic condition, into the alkaline condition. In this way, we can get rid of iridium for water oxidation and platinum for hydrogen generation. As I said in my lecture, we can generate green hydrogen use iron, nickel, molybdenum, those earth-abundant elements to make the catalyst. Instead, also under alkaline conditions, the material for the electrolyzer, the cost for those materials also can be reduced. I think if you can imagine in the near future, large-scale green hydrogen generation can become AEM-WE.
Okay, thank you. Professor Ding.
I think let me just first say the hard-to-abate sectors are foundation industry, steelmaking is one of them, biggest one, and heavy trucks, long-distance heavy trucks, probably electrification is difficult. Aviation, long-haul, probably about sort of more than 100 people, sort of passengers, jet, and and for long-distance, that's and marine, long-distance marine transportation. So those are hardest to abate sector. So for those, technologies are different. So clearly, for aviation, as I just mentioned, the hydrogen. So far, I think from what we have seen so far, the hydrogen or hydrogen vector is probably the only feasible technical route, because there might be more in the future. But I think nuclear, for example. But currently the aviation, as Mark also mentioned, because the asset strong asset is big issue. You can't just, for example, airplanes built, they should last for 20, 30, 40 years, but I think you have used them. But I think the hydrogen, probably the hydrogen vector is one of them to do that. For heavy industry, for example, steel making, cement, the in-process silt splitting probably is one of the only viable way at the moment. So the other technologies, for example, electrochemical method like Boss metal, and also the hydrogen route, hydrogen metallurgy, is a way to, it's not probably can meet the 2050 target or 2060 target. CCS is one of them, but I think it's a long way to go unless there is a radical changes. So the issue is that the disrupt technology for different areas will be different, but the hard to abate sector is very different from I agree with just most of the just mentioned, but those just the production of fuel or energy, how would you integrate that with those sectors? That's a big challenge. For example, aviation. Even you use liquefied hydrogen, thermal management, the weight, and there is many terminology. I'm not going to mention that because I happen to be involved in one of the projects, which is look at 100 passenger jet, with liquid hydrogen, and also the fuel cell technology are not there yet. Then the megawatts stack, which is currently only kilowatts, maybe 100 kilowatts stack, which is again, it's a long way to go. So just add to those, hopefully.
So there are different solutions for the sectors, but it needs a lot of scientific research and innovation. So thank you. Then our third topic is about how to ensure energy security in energy transition. I know you are here are all scientists, but that's a very practical problem.
Maybe I'll start because
I ask my question. So because of the uncertainty of weather and the intermittency behavior of renewable energy, how to ensure this, just take the power industry as an example, how to ensure the stability of the power grid is always a big challenge. And this is also the crucial reason for the difficulty to reduce the fossil energy quickly. So people talk a lot of coal power, but the grid needs stability. So then, therefore, I would like to ask your opinions about what scientific solutions we could pursue to deploy renewable energy quickly, in large scale, and affordably, while reducing the dependency on fossil energy as soon as possible. So basically, that's whether there are solutions, because we are in China, we are struggling with this issue. So I noticed Professor Ding, a lot of
I'll just do because just before I came to here, I was at the Energy and Decarbonization strategy meeting with our research council in the UK. So this is one of the areas we discussed, and so without disclosing, what's the reached. So most of thinking clearly, energy storage is one of the area, one of the aspects or measures which could enable national energy security and cost. I'll give you an example. You can't rely on importing energy. During COVID, UK import energy from Europe occasionally.
You can speak a little bit.
Occasionally, and the price is many times you could afford. So that's why we can't afford to import energy in critical time. So storing energy is crucial. So as I mentioned, the energy storage for long-term storage, for example, hydrogen, is needed, which is, I think, so far, as far as I understand, is the only economically feasible way of storing tens of hundreds of terawatt hours of energy for long term. So I think that, because I think the energy security means you probably wouldn't want to touch it, so you may only use once or twice a year. That's for sort of energy security. I think the energy storage would be one way area, particularly for hydrogen vector based. So for long-term energy storage. So that is my just input.
So you are very accurate. You mentioned this short-term, medium-term, and the long-term energy storage. I think that's a critical solution. However, the problem is the cost. So especially for the developing countries, when they don't have enough infrastructure and not a lot of firmly dispatchable power capacity, then they are encouraged to develop this intermittent renewable energy. So for long term, how to keep the stability of the power grid, I think that's a big challenge globally. Yes, Michael, please.
In Switzerland, we are fortunate. We have the mountains, and so a lot of 30% of our electricity comes from hydroelectric. And
that's the best one.
And I think in Canada they don't need any renewables. They can cover all their electric power by hydroelectric. And so if the lakes are full, we are very happy, because then we know we have about 6 months storage. And I think we should perhaps try to build also systems of this type. I mean, you can build mountains, but most countries have mountains, and so that we should think about those. This is a way to have a security.
But I remember last year when the drought happened, so Switzerland is also suffering from drought. So I saw a news
because we trusted the atomic electricity from France, and they had a breakdown of their atomic reactors. So that was a problem. That was
so uncertainty exists globally. So last year I saw a very impressive news that the mountain, the cows in Arbis are thirsty from water. So Swiss armies send a helicopter to bring water from the bottom lake to feed the cows. So even though energy security is a big problem. Yes, sorry, Ras.
Well, I think the grid systems have to be designed having a mix of energies which can compensate each other, and then we need some medium-term storage for the crisis situation, because if the grid is not designed to have sources that are balanced to each other, it's very difficult just with storage to solve the problem. For example, in Portugal, we have about 60% renewable, which is mainly wind and hydropower. But there were occasions in which wind was failed, and there was not enough hydropower to compensate. So really, the grid has to have different sources of energy that have different time periods, and we need some medium-term storage to solve these peak situations.
In China, hydropower runs about 3,000 hours per year. So that in winter we don't have. So it's a problem that hydraulic power don't have water. So that's a problem for us. I don't know whether you are more superior. So I noticed Professor Sun wants to speak something, please.
Yes, in terms of safety of sustainable energy systems, I believe it's really depend on where your country is located. And if you do have in your country wind power, solar power, or hydropower, take example of China. So China is so big. It seems we don't have such a problem in China. I take example like you put 1/3 of the, maybe less than 1/3 of the area of Qinghai province. I'm not talking about Tibet, but the Qinghai province is produce sustainable energy more than enough to sustain all the consumptions of China globally, yearly. So that seems not a big issue of sustainable energy sources in China. But in terms of turbulence or interruptions of those sustainable energy systems, again, this is a big issue we have to consider, because we don't want to make grid turbulence disturbed all the time. Although some technique can solve that problem, but they don't like to take this risk. So you need to generate something or store the sustainable energy system on site. So you should not consider put into the national grid. Rather use a local grid to produce something you can store. Solar panel generate electricity. You can use a grid for local supply for power. But what happening if you have a cloud in the sky? If you have a weather problem, if the wind stops, you need a technique to store the solar energy which can tolerate the instability of the energy sources. So I'm talking about this AMWE because it has another advantage. It can tolerate this turbulence of current density. In our lab, we have tested if you can use electricity or solar power to make artificial, manually turbulence, it's stabilized. So the current can jump from 2,000 milliamp per square centimeter down to 500 milliamp per square centimeter. Means if you have a cloud in the sky, block the sun, no problem, it still works nicely. But other techniques, what I mentioned, like alkaline electrolyzer, cannot do this. This means the operators, the machine will shut down, then start up. This causes huge technical problems. But AMWE can do this.
Professor Sun, you create my curiosity, so I would like to ask for more materials about EM from you after this event.
Okay. Happy to do
Professor Tu, please.
So I agree that to have the storage more locally instead of central, I think that can also help. Like for example, in the US, in 2021, so they put in $50 billion to develop infrastructure. And there are a lot of discussion, and even though in California right now, the biggest energy storage is the lithium battery, but that's also expensive. And then there also the talk about should we get rid of the existing, if we get rid of the coal plant and so on, or can we still reuse some of the infrastructure if we completely switch to renewable energy? And then they're also talking about maybe you can keep the existing one, and then for energy storage, you can use flow battery, something that needs a bigger footprint and nearby the existing plant. And so there are different approaches. and it's not really clear that which one will be the best, and that again depends on where you are, right? And so I think at least in California, I know right now the main energy storage is battery. Yeah.
So, but we need to, in my opinion, we need to classify short-term storage for stability of the power grid. And we also need cross-season, long-term storage for carbon neutrality. So I think we need a spectrum of energy storage technologies. However, the problem is cost. For long-term, I think for long-term storage, maybe chemical is the best media. So any comments on this topic? So I know, please, this is very free.
I think the storage technologies, I don't think they are viable at the moment for all technologies, apart from pumped hydro. Pumped hydro have specific policy across the board, I think, because it's part of grid. So, but other storage technologies, if without subsidies, and they are not viable at the moment. So really need a national policy to address that issue. So I don't have a solution. I mean, from technically, we just need to drive down the cost. Of course, while keep them safe as well. For batteries, I mean, if you keep down the cost, the more you do, probably the issues about safety can come up, because I think the real applications is not something like our research in labs. So, so yeah, I think the cost is the most important part, but I think another thing is the storage is just part of the supply chain. That can cause issues globally, because I think we know batteries, Asia is produce probably about 80% of global battery supply, the supply chain. So there's a huge amount. So that clearly will have some geopolitical issues, but it's not us as scientists or engineers to address, but it's going to be negotiation and trade negotiation between different countries. But what I'm trying to say is the cost have to depend on the policy and also trade talks between countries, particularly new emerging technology, including batteries. And of course, those technologies which are being deployed or commercial or pre-commercial stage. So we need a policy, essentially.
I agree with you. So we need not only integration of all kinds of technologies, like Professor Lee has mentioned, we also need integration of policies, strategies, and policies based on technology, based on fundamental science breakthrough. So thank you. So maybe we conclude this topic, and the next topic is about the enabling technologies that could help accelerate the energy transition. So the development of energy science and technology is closely linked with the cross-disciplinary integrated research. How do newly emerging material science or artificial intelligence and other information communication technologies foster the development breakthrough of energy technologies? So that's about ICT and artificial, etc. So I noticed Professor Lee.
Right. So I think digital technologies, AI, and also big data science all contribute to the rapid advancement of any science. So if I take my expertise as an example, so biotechnology, we can basically make not only natural chemicals, but also non-natural chemicals by designing the pathway through the computer-aided design. Now, the problem is that you don't find the enzymes to catalyze those reactions because they are non-natural. But thanks to advancement of AI, without mentioning, AlphaFold 2 and others, you can actually do the computer simulation and do the docking simulation to design very proper enzymes to perform that non-natural reactions. So these will collectively form a breakthrough technology for performing any reactions, maybe starting from CO2. So I think in the future, all these advances in artificial intelligence, machine learning, data science will drive biomanufacturing feasible and tangible. So obviously, other fields like material science, chemical engineering, all these disciplines will benefit hugely by all these, digital transformation technologies.
Yeah, that's very, very impressive. So it not only exists in the high level help for technology application, it can also be applied the fundamental study. Yes, Michael, please.
I think this is particularly important for the catalysis. I mean, catalysis helps to reduce energy losses, brings the activation energies down. And so the artificial intelligence will help us to develop better catalysts. And combined with rapid throughput screening, I think in the future we will see much better. We have seen now one example from Lee Chan-soon. I was amazed about this oxygen. You have to tell us what that compound is. And so anyway, there's room for improvement. And just think about Haber-Bosch, how much that consumes in energy. And it's just because the catalyst is not good. It's not that the reaction requires high energy. The reaction is a downhill reaction at room temperature. The formation of ammonia from hydrogen, nitrogen. So that's a real challenging reaction that we have to tackle, because the Haber-Bosch is a huge energy consumption. On a total balance, it's enormous for the fertilizer. And so if that catalyst can be, there is a better catalyst, ruthenium, but it's too expensive. So
I know the Professor Sun wants to speak something.
I think this is a very important topic. We do need people from different disciplinary to work together. So Professor Michael Gratzer mentioned the design and the catalyst. In our lab also now use AI and also computer-assisted method to screw the catalyst. We did have some useful result that to replace the platinum for hydrogen evolution catalyst. We do not go to lab, rather ask a computer and give us a lot of information. Then we go to lab and then find the good ones. So that's very important.
I think it is already, but because of new development, we can apply more. Yes, please.
I absolutely agree with both of you that the collaboration between the different disciplines very important. And one actual example I recently had was I worked with a guy who basically has great expertise on quantum dots. And I know nothing about quantum dots, except that I use microorganisms to produce them. So I collaborate with them to make a bacterium called Azotobacter, and then let them synthesize quantum dots. That's my technology. And then he analyzed the band gaps and all those, designed the quantum dot size to be favorable, and then I introduced nitrogenase. Now this bacterium producing quantum dot fixes nitrogen, convert it to ammonia. The efficiency is not quite equivalent to Haber-Bosch yet, but it showed great promise by integrating two expertise together. So I think this will become more and more important as time goes by.
So actually, this comes to my last question about international collaboration. So this morning in the opening ceremony, so Professor Nicholas Dirks, he talked about the importance and the necessity for international scientific cooperation. So my next topic is about this. So the specific question is how to proceed with the high quality international cooperation in the energy field or in the energy transition field. So I think all of you have a lot of international experiences. I would like you to share your experiences and your opinions. Another Professor too.
I think it's very important because as you can see, I think Michael and the same with my work in organic solar cells, we collaborate with people from all different continents. and share information. But in terms of what I would like to see moving forward, right? To be able to share the technology from one country to another. Did you say, for example, Vietnam and the developing country? And so if all this solar cell technology that we develop in the US or in Europe, like you mentioned earlier, there are certain renewable energy more affordable because in place like the US, but how about India? How about other places? And we share the same earth. So it would be great to be able to also collaborate with those countries and share all this the new technology that they can also implement there. Or for example, I can see that if we can have just making organic solar cell module for building integration, and but we can also collaborate in such a way that you can do scale up, we can do production in other places like India or in Vietnam or in China, right? So that could be the natural, I think, that really benefit from both countries for collaboration in that way. For us, from fundamental science, because each place, like for example, I found that in my field, all the new advanced material synthesized in China, because that's the strength that we have, that they have in China. And we collaborate with the colleague here, and we use the material that they make here and integrate into solar cell, for example. So that's a really good collaboration.
So Professor Li Xiong, Michael mentioned in his slides about your work. So you are a practitioner of
it's my pleasure to add my in practice for this cooperation. I think one of the best way for the world top cooperation is first I set myself to micro group, Switzerland, EPFL, when I start to do my research on the perovskite solar cells. And after I returned back to China and set up my own research group, I also sent my student, PhD student, to micrograduate group for the in-depth research, in-depth collaboration. And in recent years, myself and also my PhD students can collaborate with my graduate to publish very important research, and also has some top published in the science journal. So what I want to say is that one of the best way for the collaboration is the talent exchange and for the talent training. Thank you.
Thank you. So we are running up our time. Yeah, so
I think one of the things that speaks for international collaboration is that we have different approaches, different cultures. I realize that in Germany it's very systematic, and some other cultures they take a more, what should I say, inspirational approach. And so when the two cultures meet, that's when the breakthroughs are made. And so I can say that with, like Li Xiong just mentioned, our collaboration. It's very beneficial. And if we build up walls, that will be terrible. It will never happen with Switzerland. We know we need it to be open.
Yeah, in my learning, to access to knowledge is a privilege. But without this privilege, then the science development will be much slower. So we need to combine the wisdom of the whole humankind. I think that's the meaning for international collaboration. So unfortunately, we are running up our time. So I would like, I don't make a summary. I would like to invite Michael to give a summary speech.
Yeah, so it's clear that we started with first of all, the energy supply and the sources of CO2 that are difficult to abate, and then how can we replace, for example, jet fuel? So I think what emerges here is that first of all, the multidisciplinary approach is very important. And it's also clear that electricity alone cannot do it. So we need electrochemical storage. And so the examples given with the anion exchange membranes was very telling. And so this storage will probably, the vector will be hydrogen in the first place. But there may be other compounds like if you reduce nitrogen to ammonia, ammonia could become a vector. And so these are challenging problems which I think we can now tackle with artificial intelligence much better in the catalytic sense. That we finally get a nitrogen reduction catalyst that works well. As I said, it's a spontaneous reaction thermodynamically, but it takes many hundreds degrees in reality now with the Haber-Bosch process. So yeah, and finally, with the international collaboration, I think it's a must. We would not move forward with these challenging problems unless we use all the brains in the world. And we have different approaches and different cultures, but we can benefit from being open. Thank you.
Thank you. So before I conclude this panel, I would like to invite all the audience to give a warmful applause for our panelists for their wonderful sharing. Yeah, Professor Zhang. So I think we need to have a photo together. To memorize this moment, we need to have a group photo.